In this tape, we're going to be studying anti-differentiation. If I were to tell you that y is equal to x squared plus 3x plus 5 and ask you to find derivative of y with respect to x, dy dx, and of course you would tell me the derivative of y with respect to x is 2x plus 3, this process is known as differentiation. On the other hand, if I were to start with dy dx, I say dy dx is 2x plus 7, and I ask you what y equals. Going from the derivative back to the function, which is started, let's see, just from experience, you might be able to come up with the answer here. Maybe you would say, well, x squared will give me the 2x, 7x. Somebody might say x squared plus 7x plus 4, and I'd have to say yes. The derivative in that case would be 2x plus 7. Somebody else might say x squared plus 7x minus 5. And I have to say, yep, that's also a possibility. The derivative is 2x plus 7. What about x squared plus 7x plus the square root of 3? Also good. So what I could write for the most general antiderivative in this case would be x squared plus 7x plus some constant c. This covers all these possibilities. The derivative is going to be 2x plus 7, and since the derivative of a constant is 0, we will have the correct derivative. And this covers all the various answers that you might give me. So we'll say the most general antiderivative of 2x plus 7 is x squared plus 7x plus c. This procedure, going from the derivative back to the function, is known as anti-differentiation. And later on, it's also going to be called integration. Okay, but right now, we're calling it anti-differentiation. And basically, it's the procedure of undoing differentiation. Now, this is an inverse operation. Any inverse operation is generally more difficult to learn than the original operation. When you learned how to subtract, most of you had more trouble with subtraction than with the original operation of addition. Same thing, division for most of you is more difficult to master than multiplication. And it's going to be the same thing here. Right now, it doesn't seem like a big deal. You say, well, I can do this, I can do this. When you started to multiply and divide, 4 times 2 is 8, 8 divided by 2 is 4. When the divisions got more complicated, there was a certain amount of guesswork. You looked at a long division problem. Did you say, oh, well, does it go 6 times? No, you tried it. No, you tried 5 times. This was before calculators, okay? And there was certainly a certain amount of guesswork. Here, too, when the problems get more complicated, anti-differentiation is going to be significantly more difficult than differentiation. In the beginning, we don't really have that. Okay, now, this is a little awkward writing dy dx and then writing y. We'd like a symbol that would indicate that we're going to take the antiderivative. And the symbol is as follows. There is an integral sign, and then we write 2x plus 7, and then dx. This should be read an antiderivative of 2x plus 7 with respect to x. Antiderivative of 2x plus 7 with respect to x. And the answer is written x squared plus 7x plus c. So just like the symbol dy dx, this is really derivative of y with respect to x, the d indicating differentiation, and this indicating with respect to x. The derivative is really like the derivative of y with respect to x. We say dy dx, but it's a derivative of y with respect to x. The same thing here. This is indicating anti-differentiation with respect to x, and we're anti-differentiating 2x plus 7. We're asking ourselves, if this is the derivative, what must the function have been? What must the function be? Now, we can always check this very simply. Take the derivative of your answer, and if you've done it correctly, you should get the 2x plus 7. What do you have to differentiate to get 2x plus 7? And the answer is x squared plus 7x plus c, and we check it by differentiating. Okay. Okay. Now, what if I ask for antiderivative of x cubed with respect to x? What do you have to start with to wind up with the derivative of x cubed? Well, we know how differentiation works, and when you're differentiating a polynomial, generally the degree goes down. So we started with x to the fourth. What would be the derivative of x to the fourth? 4x cubed. We only want x cubed. So if we said x to the fourth over 4, we would have the right answer, because the derivative here would be 1/4 times the derivative of x to the fourth, 1/4 times 4x cubed would be x cubed would work out. And we can use this to get a general formula for the antiderivative of x to the n with respect to x. Following this pattern, it's going to be x to the 1 more power over that power plus c, assuming that n is not minus 1. Because if n were minus 1, we'd have division by 0. This is going to be our basic anti-differentiation formula for anti-differentiating polynomials and other functions. And to check this, what is the derivative of x to the n plus 1? Well, that would be n plus 1 times x to the n, which would be n plus 1 times too big. So if we divide by n plus 1, the derivative will come out to be x to the n, which is just what we want. So the antiderivative of x to a power is x to the 1 more power over that 1 more power plus c. Now, if we use this as a basic building block, we'll be able to handle more complicated problems. Okay, so here goes. Antiderivative of 10x to the fourth plus 8x cubed plus 6x squared plus 4x plus 5 with respect to x. Okay. Now, some of you may be able to guess the answer in this case. It gets a little bit more complicated, a little more difficult. So it's good to have a bunch of rules set up that we could follow. One rule that I'm going to tell you about is that instead of anti-differentiating this big polynomial here, we can break it up into 1, 2, 3, 4, 5 smaller problems. We can make it the antiderivative of 10x to the fourth with respect to x, plus the antiderivative of 8x cubed with respect to x, plus the antiderivative of 6x squared with respect to x, plus the antiderivative of 4x with respect to x, and the antiderivative of 5 with respect to x. We break it up into 5 smaller problems. Now, the next thing that we're going to do is, in each case, instead of worrying about the constant, I'm able to pull the constant out in front of the antiderivative symbol. Constants, and only constants, can go back and forth through the antiderivative symbol. So instead of the antiderivative of 10x to the fourth, I'll make it 10 times the antiderivative of x to the fourth. And then instead of the antiderivative of 8x cubed, 8 times the antiderivative of x cubed, 6 times the antiderivative of x squared, 4 times the antiderivative of x, plus now antiderivative of 5, antiderivative of a constant. Okay, we're going to come back to that in a moment. Let's just leave it antiderivative of 5, and we'll come back to that in a moment. Okay, now, each case we're left with the problem of anti-differentiating x to a power. This is really x to the first power. So if we go back to our rule that we had, antiderivative of x to the nth power is x to the 1 more power over that power plus a constant. We're going to be able to handle this. 10 times, now what is the antiderivative of x to the 4? It's x to the 1 more power, x to the 5 over 5 plus, now there's 5 different problems here, so I'm going to use a different constant each time, plus say c1, plus now 8 times antiderivative of x cubed, which would be x to the 4 over 4, plus constant, let's say c2, plus 6 times antiderivative of x squared, which is x to the 3 over 3, plus another constant, plus 4 times antiderivative of x to the first, which is x to the 2 over 2, plus a fourth constant, plus, now, antiderivative of 5. Let's go over here. Let's consider the problem of the antiderivative of a constant. Remember, we're talking about the antiderivative of 5. What do you have to start with in order to have a derivative of 5? Well, common experience tells us 5x plus some other constant. What's the derivative of 5x plus a constant? Of course, that's 5. Derivative of a constant is 0. Derivative of 5x would just be 5. And if k is an arbitrary constant, then antiderivative of k with respect to x would be kx plus another constant. And this k and c are constants. K and c are constants. Okay. Another way of looking at this, remember I said before, I said you could either pull the 5 out or not. Let's say you chose to pull the 5 out in front. We went this way. It could be 5 times the antiderivative of 1 dx. You could think of this as 5. Now, antiderivative of x to the 0, because x to the 0 is the same as 1. And then you could do it like all the other parts of the problem. 5 x to the 1 over 1 plus a constant, in which case you'd still get back to the 5x plus c. So before I said it doesn't matter whether you pull the constant out. If it's just a constant by itself, you can either pull it out or leave it in. This is true. Either you say the antiderivative of 5 is 5x plus a constant, or you think of this as 5 pulled out in front times x to the 0, which gets anti-differentiated the same way all the other ones, x to the 1 over 1 plus c. Okay, so we have this over here now. The antiderivative of 5 with respect to x back here is 5x plus another constant, let's say c5. Let's clean this up a little. Let's see what we have. 10x to the 5 over 5 plus 10c1 plus 8x to the 4 over 4 plus 8c2 and so on. I'm going to pull the constants out till the end. So let's first collect the terms involving x. So it's 10 x to the 5 over 5 plus 8 x to the 4 over 4 plus 6 x to the 3 over 3 plus 4 x to the 2 over 2 plus 5x plus, now, what did we have for the constants? We had 10c1 and 8c2 and 6c3 and 4c4 plus c5. And you know something? We don't have to bother with all these constants. What is this saying? 10 times some arbitrary constant, plus 8 times some other constant, plus 6 times a third constant, plus 4 times a fourth, plus a fifth. All of this could be replaced by just one simple plus c at the end of the problem. Okay? So we don't have to worry about the intermediary constants that we get. So let's see what we have. The antiderivative of 10x to the fourth plus 8x cubed plus 4x plus 5 gives us this plus c. Let's clean this up a little. What do we have for a final answer? 2x to the fifth plus 2x to the fourth plus 2x cubed plus 2x squared plus 5x plus c. This is our answer to this problem. Let's check it. If it's correct, when you differentiate this, you should get what you started with originally. I was asking for an antiderivative of this polynomial, something which when you differentiate will give you this polynomial. Okay, let's see if we found it. Let's differentiate our answer. What is the derivative of 2x to the fifth plus 2x to the fourth plus 2x cubed plus 2x squared plus 5x plus c. And the way we differentiate polynomials, constant times the power, x to the 1 less power straight across. So 2 times 5, 10. X to the 1 less power. 2 times 4, 8. X to the 1 less power, 8x cubed. Plus 6x squared plus 4x plus 5x to the 0 or plus 5, and the derivative of a constant is just 0. So 10x to the 4th plus 8x cubed plus 6x squared plus 4x plus 5, which is exactly what we started with. So we have done this correctly. This is correct. Now, most of you can differentiate in one step like this. Okay, and you might wonder, can you also anti-differentiate in one step, or do you have to go through all of these stages? The answer is yes, you can immediately leapfrog to the answer, as long as you remember what you were doing. I was breaking it up into 5 smaller problems. Okay, in other words, I'm going to be able to do it piece by piece. In each case, I pulled out the constant, and then I said, how do you anti-differentiate x to a power? It's x to the 1 more power over the power. So in each case, I got the constant, x to the 1 more power over the power, the constant, x to the 1 more power over the power, and so on. So we can go straight through to this. How do you anti-differentiate a polynomial? It's the constant 10, x to the 1 more power, 5 over 5, plus the constant 8, x to the 1 more power, x to the 4 over 4, plus the constant 6, x to the 1 more power, then 1 more than 2, x to the 3 over 3. Constant 4, this is really 4x to the 1, so 4x to the 2 over 2. And now how do you anti-differentiate it? 5, either 5x plus c, or you think of it as 5x to the 0. So it's 5x to the 1 over 1 plus c. So yes, you can jump right across to the answer. Okay, for our next example, let's try antiderivative of 3x squared plus 2x plus 4. Now we know that we can do it term by term. So each case it's going to be a constant 3, x to the 1 more power over that power, plus the constant 2, x to the 1 more power over that power, plus the antiderivative of 4. Once again, the antiderivative of a constant is just the constant times x plus c. So the antiderivative of 4, 4x plus c. And cleaning this up, we get x cubed plus x squared plus 4x plus c. And have we done it correctly? Yes, because the derivative here is 3x squared plus 2x plus 4, which is what we started with. Okay, well, this works fine for polynomials. What if we don't have a polynomial exactly, but we have something like this? 6 over x to the 4th plus 3 over x squared. Now this isn't a polynomial, because a polynomial is a sum of terms, each one of which is a constant times the variable to a power, where the power is a non-negative integer. This can be almost written like a polynomial if you didn't insist that the integers be non-negative integers. So I could write this as 6x to the minus 4 plus 3x to the minus 2. Still a sum of terms, each one of which is a constant times x to a power, but the powers are not necessarily non-negative integers. We're allowing different types of powers. But the rule still holds. We can go straight across, each time taking the constant, x to the 1 more power. Now be careful. When you have 1 more than 2, you add 1, and you got 3. 1 more than 1 was 2. 1 more than a negative number, you're still going to add 1. But when you add 1 to minus 4, you get minus 3. And you divide by that power. 3x to the, now add 1 here. You get to the minus 1 power. Divide by that power plus c. So just like before, I'm adding 1 to the power. But you have to just be a little bit more careful with the algebra here. Adding 1 gives you -3, and you divide by the new power. Adding 1, you get -1, you divide by the new power. Now this is the correct answer. The question is, can we simplify this at all? Now why would we want to simplify it? We are getting to a stage where we're going to want to substitute values into our antiderivative. Okay? It's not as convenient when you have negative exponents. So let's see what we can do here. First, 6 over -3 is -2, so it's -2x to the -3. 3 over -1 is -3. -3x to the -1 plus c. Well, that's a little bit better. Still better would be to rewrite this as -2, instead of x to the -3, -2 over x cubed, -3 over x plus c. This is a nice form. If I had to substitute, for example, x equal to 2 or x equal to 3 in, I'd rather have it in this form than, say, this form or even this form. This would enable me to plug in a value for x a lot easier. Be careful, when we use the fact that x to the -3 is 1 over x cubed, only the x drops down. The -2 stays in the numerator, the -3 stays in the numerator. X to the -3 goes downstairs as x cubed, x to the -1 goes downstairs as x to the 1, or just x. Okay, for our next example, let's try this. 5x to the 4th plus 4x squared minus 7 times the square root of x all over x squared. You have to anti-differentiate this. I'll tell you what you can't do. You can't anti-differentiate the top and divide by the antiderivative of the bottom any more than you could differentiate that way. Okay, what you can do here is to try to get it into this sort of polynomial type form like we had in the last example. Make use of the fact that a plus b plus c over d can be rewritten as a over d plus b over d plus c over d. Usually we go in this direction. We say we want to add fractions with the same bottom. We combine the numerators over the common denominator. For example, if we wanted to add 2/10 plus 1/10 plus 3/10, we'd say 2 plus 1 plus 3 all over 10. But there's no reason that we can't go in this direction as well. And this particular problem, it's to our advantage to break it up and to do that. So instead of a plus b plus c over d, I'm going to make it a over d plus b over d plus c over d. 5x to the 4th over x squared plus 4x squared over x squared minus 7 times the square root of x over x squared dx. Using the fact that a plus b plus c over d is a over d plus b over d plus c over d. You can only break up tops. You cannot break up bottoms. Okay. Now, let's make use of the fact that x to the a over x to the b is x to the a minus b, one of our rules of exponents. So 5, x to the a over x to the b is x to the a minus b. It's x to the 4 minus 2 plus 4. X to the a over x to the b is x to the a minus b. 2 minus 2 minus 7. X to the a over x to the b. You may say, how is that x to the a? The square root of x is really x to the 1/2 power. So I rewrote the square root of x as x to the 1/2 power. So now it's 7 x to the a over x to the b. So once again, x to the a minus b. So now, we're doing a lot of work. We haven't anti-differentiated yet. Don't judge your problem by how much work you've done. We're just rewriting this into a better form. We have yet to do the anti-differentiation. Let's clean this up a little bit more. What do we have? Antiderivative. 5x to the 4 minus 2, 5x squared, plus 4x to the 0. X to the 0, of course, is just 1. minus 7 x2. Now, 1/2 minus 2. 1/2 minus 2 is really 1/2 minus 4/2, combining over the common denominator, giving us 1 minus 4 minus 3/2. 1/2 minus 2. 1/2 minus 2. 1/2 minus 4/2 minus 3/2 power. Now we're ready to start the problem. All of the work we've done so far, breaking it up, putting each term over the same denominator, combining x to the a over x to the b, making it x to the a minus b, was all to put it into this polynomial type form, a sum of terms, each one of which was a constant times x to a power. But the power does not have to be just a non-negative integer. Now we're ready to anti-differentiate. Now we're first going to do that. So we go straight across the constant 5x to the 1 more power over that power, plus 4x to the 1 over 1, minus 7x2. Now add 1 or 2/2, so we have minus 1/2 over minus 1/2 plus a constant. Or 5/3 x cubed plus 4x. Now, minus 7 over minus 1/2, it's plus. Minus over minus is plus. Instead of dividing by 1/2, we can invert and multiply by 2 over 1, so it's plus 14. X to the minus 1/2 plus c, and we can finish this up as 5/3 x cubed plus 4x. This was plus. Instead of dividing by 1/2, we invert and multiply by 2 over 1, so 14x to the minus 1/2, which we'll rewrite as 14 over x to the 1/2, or over the square root of x plus c. Instead of 14x to the minus 1/2, 14 over x to the 1/2, and then rewrite x to the 1/2 as the square root of x. This is a convenient way if we wanted to substitute a value for x in. Okay, so far we have a way of handling x to a power to anti-differentiate x to the 1 more power over that power plus a constant, assuming the power is not minus 1, and how to anti-differentiate a constant. For our next formula, I'm going to show you how to anti-differentiate a function to a power followed by exactly its derivative. You may say, it's a little strange setup. Okay, I'm not saying it happens every second, but if you happen to have a function to a power followed by its derivative, the answer will be the function, the antiderivative will be the function to the 1 more power over that power plus a constant, once again assuming n is not minus 1. We're going to discuss this in detail, but first let's just see if you follow this. If you happen to have a function to a power followed by exactly derivative of this function here, then antiderivative is a function to the same function, more power over that power. Let's try an example, see if it works. Antiderivative of x squared plus 3 to the 10th power times 2x with respect to x. This is what I mean by a function to a power followed by exactly the derivative of what you were raising to the power. This falls under this category. Function to a power. Remember I said if you have a function to a power followed by exactly the derivative, it's going to be the function to the 1 more power over that power plus c, assuming the power is not minus 1. So here f of x is the x squared plus 3, and then the derivative of this is exactly 2x. So we have exactly what I said, and we have x squared plus 3 to the 1 more power to the 11th power over 11 plus c. Now, unlike differentiation formulas, each one of which has to be proved separately, to prove that the anti-differentiation works, all we have to do is differentiate the right-hand side and see that we get this. Let's check it. What is the derivative of 1/11 x squared plus 3 to the 11th plus c. Instead of dividing by 11, I wrote this 1/11th x squared plus 3 to the 11th. Okay, so it's a constant times a function. The derivative is the constant times the derivative of this function. Now, what is this? This is x squared plus 3 to the 11th power. How do you differentiate something to a power? It's the power times x squared plus 3 to the 1 less power times the derivative of the inside. There's your chain rule. Now, the derivative of the constant, of course, is 0. The 11s cancel, and we have x squared plus 3 to the 10th times 2x, exactly what you started with. So now we understand that this is not as artificial as we might have thought originally. When you differentiate a function to a power by the chain rule, it produces, over here, the derivative of the inside. In other words, power function, 1 less power, times the derivative of the inside. Since anti-differentiation, we want to undo the differentiation. In order to undo the chain rule, we have to start with the function to the power times the derivative of the inside. Then, and only then, can we get the function to the 1 more power over that power plus c. Okay, now, what if we didn't have the 2x here? If we didn't have the 2x here, we would have had to multiply x squared plus 3 times itself 10 times, get this humongous polynomial, and anti-differentiate term by term, which would not be terribly pleasant. But if we're lucky enough to have the x squared plus 3's derivative 2x right here, then we can just reverse the chain rule and get antiderivative of a function to a power followed by exactly its derivative, the function to the 1 more power over that power plus c. Okay. Let's try another example. Suppose we had antiderivative of x to the 4th plus 3 to the 8th times x cubed. Well, if we put this in the category function to a power, the derivative of the x to the 4th plus 3 is 4x cubed. We don't have exactly the derivative of the function. In other words, we're trying to match this to a function to a power followed by the derivative of the inside. Then we can say it's the function to the 1 more power over that power plus c. And I said we could only do it if we had right next to it the derivative of the x to the 4th plus 3. We don't have that. Because if f of x is x to the 4th plus 3, then the derivative is 4x cubed. Turns out it's not that bad. I sort of lied. You don't have to have exactly the derivative right next to it. You are allowed to be off by a constant. If you're off by a multiplicative constant, I can fix it. Okay, let's see if we can do it. Here, we were dealing with antiderivative of x to the 4th plus 3 to the 8th times x cubed dx. Now, I really wish this was 4x cubed. Well, I can make it 4x cubed. I multiply by 4. Except you can't go around multiplying by 4 unless I also divide by 4. Okay, so I am multiplying by 1. I don't know if it comes out in blue here, but I'm multiplying by 4 over 4 in blue. Now, the 4's cancel, we're back where we started. But if we don't cancel the 4's, if we leave this, I'm going to leave this 4x cubed in here. You see the other 4 here? I'm going to move that outside in front. I can do that because I am always allowed to move constants back and forth through the antiderivative sign. Constants and only constants. We did that earlier today when we said the antiderivative of 10x cubed was 10 times the antiderivative of x cubed. We pulled the constants out in front. Well, we can do it here too. I'm going to choose to pull the bottom 4 out in front, make it 1/4 antiderivative of x to the 4th plus 3 to the 8th power times 4x cubed dx. Now you may say, well, why don't you also take this 4 out? I could. If I take this 4 out, it will cancel this 4. I'll be back where I started. I like it the way it is. The 1/4 in front, this is now a function to a power followed by exactly the derivative. I didn't have it originally, but I have it now. So we have 1/4 function to a power followed by exactly its derivative. We could have taken the other 4 out and go back where we started, but we don't want to. We want to leave it like this. So it's 1/4. And now here we have exactly what we want, a function to a power followed by exactly the derivative. So we're going to get the function x to the 4th plus 3 to the 1 more power over that power plus a constant for a final answer of x to the 4th plus 3 to the 9th power over 36 plus c. Okay, so let's see what we have so far today. We have formula for anti-differentiating x to the n for a constant, and this new formula for a function to a power followed by its derivative. Now, the notation here is not fabulous. Let's see if we can clean it up a little bit. We have antiderivative of f of x to the nth power times f prime of x dx. And we have written it as f of x to the n plus 1 over n plus 1 plus c if n is not minus 1. There's nothing wrong with this formula, but it turns out there is a better way that we could write it. Let's make a substitution. Let's let u equal f of x. Wherever I see f of x, I'm going to think u. Okay. Then, what would du dx be? The derivative of u, du dx, would be f prime of x. U is f of x, du dx, derivative of u with respect to x would be f prime of x. And if we think of this differential, if we multiply both sides by dx, then du is f prime of x dx. Okay, just cross multiply. If you haven't gotten to this in your classes, you will be discussing differential notation. And even though this is derivative of u with respect to x, it could also be thought of on another level as du divided by dx. So du is f prime of x dx. Let's try to clean this formula up a little, see what happens. This would become the antiderivative of f of x, which is u, to the nth power. Now, f prime of x dx, that's just your du. And that's going to be u to the n plus 1 over n plus 1 plus c, if n is not minus 1. Whereas once again, f of x, I'm calling that u. Following this through, then du dx would be f prime of x, and du would be f prime of x dx. And this would clean up to the antiderivative of u to the n, du, is u to the n plus 1 over n plus 1 plus c. And this is the way I'm going to recommend you memorizing the formula. Now, turns out that if you memorize it this way, it can do double duty. It can give you this formula and this formula as well. It's sort of like a cartoon that is understandable on two levels. Children watch it and they see it one way, and an adult watches it and sees certain things that obviously the children are not understanding. It's meant for both children and adults. Well, here we have a formula that's good on two levels. On the child's level, if u is x, all I have changed is the letter, and obviously if we replace u by x and du is dx, we'd get this formula. Instead of u to the n du, we have x to the n dx, and it's just giving you x to the n plus 1 over n plus 1 plus c. So on one level, this formula is the same as this. But on the other level, on the adult level, if we think of u not as just x, but as a function of x, and then du is f prime of x dx, it's also giving us this other formula here. And it's going to be very convenient to have this u notation. All of the formulas that we're going to have for anti-differentiation will have a level with x and a level involving a function of x. And this notation will enable us to learn half as many formulas and still get everything we need. Okay, let's try this on one of our problems. Let's say we want to anti-differentiate x squared dx over the square root of x cubed plus 4. I can write it this way. Sometimes you'll see dx as part of the numerator. Sometimes you'll see it written next to the problem over here. It's still, the dx is considered part of the numerator. Why am I specifying this now? Because in this notation, dx has a different meaning. Before, dx just meant with respect to x. In the differential notation, du is f prime of x dx, and I need it exactly that way. So all of a sudden, the dx is going to be more directly involved in the problem. Okay. First thing you may say, what is this? Where did the square root come from? Well, let's rewrite it. Let's bring up, this is really x cubed plus 4 to the 1/2 power. Let's bring it up and make it x cubed plus 4 to the minus 1/2 power times x squared dx. And we're trying to match to our new formula, which is u to the n du. To anti-differentiate, you get u to the n plus 1 over n plus 1 plus c, if n is not minus 1. So what are we going to do? Instead of letting f of x be x cubed plus 4, we're going to let u be x cubed plus 4. Same idea. Then what's du dx? Du dx is 3x squared, and du, the differential of u, is 3x squared dx. So this is almost in the form u to the n du, but not quite, because du is 3x squared and dx, and we only have x squared dx. But just like we handled it before, I am going to multiply by 3 over 3. In other words, I am multiplying by 1. Okay? This is something I'm allowed to do. I'm always allowed to multiply by 1. The 3's will cancel. You're back where you started. But I want to leave it this way. And the 3 on the top I'm going to keep. The 3 on the bottom I'm going to move outside. And the antiderivative of x cubed plus 4 to the minus 1/2 3x squared dx. Now, this is 1/3 antiderivative. Now, u is x cubed plus 4. Du is 3x squared dx. So this is really u to the minus 1/2 du. 1/3 u to the n du, exactly. So to anti-differentiate, 1/3 u to the 1 more power, add 1, so minus 1/2 plus 1, 1/2 over the new power plus c. Okay, instead of dividing by 1/2, we invert and multiply by 2, so 2/3 u to the 1/2, or the square root of u plus c, or 2/3 the square root of, now, if someone gives you a question in x, give them back an answer in x. Okay? This is a question. I want you to give me something whose derivative is equal to this. U is something we instituted here. We put this in to help us with the problem, but the final answer should not have u in it. Okay, u is x cubed plus 4. So it's 2/3 the square root of u is 2/3 the square root of x cubed plus 4 plus c. Okay, for our last example, let's try this. Antiderivative of 12x squared plus 3x to the 4th power times 8x plus 1 dx. Now, the formula that we're going to try to match to is, of course, antiderivative of u to the n du is u to the n plus 1 over n plus 1 plus c if n is not minus 1. Now, to match this, u should be 12x squared plus 3x. This would be u to the n would be 4. Du dx, derivative of u with respect to x, would be 24x plus 3. And cross-multiplying du would be 24x plus 3 dx. Okay, now at first glance you may say, hey, wait a minute. I'm off by more than a constant. This doesn't look like this. We have 8x plus 1. But if you think about it for a few moments, 24x plus 3 is really 3 times 8x plus 1 dx. So even though it might not have looked at first glance, du, 24x plus 3 dx, is really 3 times 8x plus 1 dx. And we are only off by a multiplicative constant, namely 3. So we're going to multiply and divide by 3, multiplying by 1. That's the net result. We're going to keep this 3 here, move this one out in front, and give us 1/3 antiderivative of 12x squared plus 3x to the 4th times 3 times 8x plus 1 dx. And under our substitution, this cleans up into 1/3. Now, 12x squared plus 3x is u. So this becomes u to the 4th. And this thing here, 3 times 8x plus 1 dx, is just du. So this becomes 1/3 antiderivative of u to the 4th du, or 1/3 u to the 5th over 5 plus c. How do you antidifferentiate u to the 4th? With respect to u, it's u to the 5 over 5 plus c. So you get 1/15 u to the 5th plus c. Going back to x, the original variable, 1/15 u to the 5th plus c, where u is 12x squared plus 3x. And that is the end of the problem and the end of the videotape.